Hi, let's continue with the regular grammar. We were discussing about regular grammar in the previous video. We have seen what is regular grammar. We have seen what are the possibilities of your regular grammar production rules. Like I have discussed that every production will have the structure of like x derives y will have, if suppose there is a production x derives y, so this side will always be a non-terminal and the right hand side can be epsilon. It is sometimes written as lambda also. Okay, so generally it is epsilon. So right hand side can be epsilon, or we can have a terminal followed by non-terminal, or non-terminal followed by a terminal, but a single terminal followed by single non-terminal, and or single non-terminal followed by a terminal. And then we have seen what is right linear grammar, and we have seen left linear grammar also. So if in the production, like your non-terminal is at the leftmost side, like suppose here it is a and it is y, so this one is the rightmost side, rightmost position, so it is right linear grammar. It is right linear grammar. And if suppose in your production it is like y a, so it is on the leftmost side, leftmost character or leftmost symbol is the non-terminal, so it is your left linear grammar. Okay, so now see, let us see how to convert the finite automata to regular grammar. Okay, and then we'll move on. So see here, we'll see conversion of finite automata to regular grammar. So let us take an example where finite automata for accepting strings that starts with 1. So you are given a finite automata, finite automata for accepting strings that starts with 1. So let us draw the finite automata first. And you suppose that it is already given to you, like this is the starting state. Starting state generally it is taken as q naught or a or b. So I am taking here as m, and it is accept for all accepting strings that starts with 1. So it should start with 1, and then let us write the final state like this one. So this is your final state. So by accepting 1 only it can reach to final state, and it can take some other characters 1 or 0, because the alphabet is 1 and 0. So we can, what we can write about this finite automata, that the initial state is m, final state is n, and the alphabets are 1 and 0. Okay, alphabets given is 1 and 0. Alphabet is the set of characters, input characters, so it is 0 and 1 or 1 and 0. The initial state is generally starting state. It is given as m, and the final state is given as n. Okay. Now, see, the regular grammar corresponding to finite automata is how we find it. See, from m, since the starting state is m, so we start from m. Okay, we start from m, and on 1 it is going to n. It is going to n. From m, on taking the symbol 1, it is going to state n, and it is also a final state, so we can write m goes to 1 also, only 1. Okay, that means it is reaching to the final state. Okay, or we can just write um, By removing this line, we can write n derives epsilon, because it cannot, it is 1 0, it is a self loop, so it is a star actually. Clean star means without taking anything, it is reaching to the state also. Or it may take 0 and reach to n, or it may take 1 and reach to n. So we have three alternatives for n. We can combine all three in one. We can combine all three in one. Like we write n derives epsilon, or 0n, or 1n. We can write this. For m we have 1n. Okay. So this is your right linear grammar. Yeah, this is your right linear grammar for the given finite automata. So we have this thing that the finite automata is given, and we can find the right linear grammar for this finite automata directly. This is right linear grammar. Okay. But suppose if we want to find the left linear grammar for this, how we can do this? Let us see. If we just reverse the grammar, if we just reverse the grammar, every production rule, like m derives 1n, so let us write n1, and n derives epsilon, or n0, n1. This, if you find it, this is now left linear grammar. But if you observe this is the language which is saying that it will take all the strings which ends in one. But in our given language, it was set of all strings which was starting with one. Set of all language starting with all strings, set of all strings starting with 1. But here, when we have directly reversed it, it is now the language is also reversed, means we are getting L dash. The language is containing all the strings which is ending with 1. So how we do now? Now see. So what we have to do this, for this, to find the LNG for this, yani it means L left linear grammar for this finite automata, we have to reverse this finite automata first. So let me reverse the diagram of this. So, and this is M, and this is N. What we have to do in reversing the finite automata? We have to make the initial state as final state and final state as initial state, and reverse all the transition. Earlier M was the initial state, make it final, N was the final, so make it initial, and reverse the transition. So the one was going from this way, make it this way, and now this will remain as it is. Self loop will remain as it is. Okay. Now when we write this grammar, how we will write? We will write n derives 0n, or 1n, or epsilon. Okay. Sorry, not epsilon. It will be from 0n, 1n, and this one will be 1m. It is going to the final state, and m is epsilon. On m it is epsilon. Now, now reversing the above right linear grammar. This is right linear grammar. This you have got the right linear grammar. Now reverse this. So what we get, n derives n0, n1, m1, and m derives epsilon. Okay. So this is the LLG. This is the LLG for our given language. This is the LLG for our given language. This was earlier what we were doing, we were just reversing the RLG which we have got from the finite automata. So we were getting the reverse, or you can say the complement of the language. Okay. So if we want to find the LLG for the finite automata, reverse the finite automata first and then write its right linear grammar and then reverse it. Then you will get the left linear grammar for that finite automata. Okay? Okay, thank you. Thanks for watching.